one is this scenario. Okay, so this is a swing. Those of you that are at home, there's the swing. It's going back and forth, and back and forth, and back and forth. And some of you guys might just start to feel very, very sleepy very, very soon. And the reason why this can be modeled with a sinusoidal function is that a swing or a pendulum, basically the path is cyclical, right? It starts up at sort of a maximum height, and then it goes down and it reaches its minimum height, and it goes back up and gets to a maximum height, and then it continues along that same path and goes down to a minimum height, and goes back up, and then goes back down, and goes back up, and then goes back down. And that height pattern, right, is cyclical, okay? So the height above the ground of the bottom of the pendulum or the bottom of the swing, which is where the person's gonna sit, is cyclical. And so it can be modeled using a sinusoidal function. Okay, so we're gonna look at one of these. For a physics project, Morgan and Lily had to graph and analyze an example of simple harmonic motion. Morgan swung on a swing and Lily used a motion detector to measure Morgan's height above the ground over time as she swung back and forth and back and forth and back and forth. The girls then graphed their data as shown below. At the end of each cycle, the swing returned to its initial position, which resulted in a sinusoidal graph. Okay? So what this graph is looking at is the height of the graph, the height of the swing, rather, as time in seconds passes. Okay? So, first question, how far above the ground was the swing that the girls used? So here's the swing. So it's going back and forth and back and forth. The height above the ground, what's that going to correspond to on the graph in terms of the height? What do you think? The min, yes, exactly. Because when you're at the bottom of the swing, which is the minimum height that you could possibly be, that's when you're directly above the ground. Exactly. Good. Okay, so how far above the swing? Well, we've got to look at where the min value is, right? So that's about here. Oh, shoot. Smartboard again. Okay, hopefully this will work. That's about here. So you got to look at your scale, right? So 4 blocks represents 1 meter. This is slightly above 3 blocks. So 3 blocks would be like 75 centimeters. So maybe it's like 80 centimeters. Does that make sense? Yes? No? The scale? Yeah. Good? No? Can I get some nods from the crowd? Don't nod if you don't mean it. Yes? No? Okay. Right. So 0 meters, 1 meter. Each of these is 1/4 of the meter. So this would be like 0.25 meters, 0.5 meters, 0.75 meters. That's 1 meter. This is a little bit above 0.75 meters, so maybe it's about 0.8 meters. Okay? If you're a little bit off there, that's okay. You have to use your judgment. Okay? So let's say it's about 0.8 meters. Okay? What characteristic of the graph does it relate to? It's the min value. Okay? How long does it take for Morgan to complete 1 full swing? Let me bring the graph back. What do you guys think? Take a look at the graphs. How long do you think it's going to take for her to complete 1 full swing? Yes. 1.5 seconds. So a couple of you had your hand up. How many people agree it's 1.5 seconds? Okay, quite a few of you. 1.5 seconds is right here. So we start at a max, we get back to a max. Okay, now I thought that too the first time I looked at this problem. And then I had to kind of reconsider, because in my mind, one full swing, maybe I'll turn it this way too, is you start on one side, you go all the way to the other, which means you reach the maximum height again, yes? Then you go back to where you started. That's one full swing. Does that make sense? Okay. How many times do you actually reach the maximum height though? Start on the other side, that's once, and then back to the start. That's twice, yes. So 1.5 periods to get to here is actually going to go from when someone's pulling you back, like who's on the swing? Morgan? Morgan's on the swing. So maybe Lily's the one who's holding her back here and then letting go, and then she's going to go all the way to the front, to the 6-meter point, right? That's where she is at 1.5 seconds. So this is at the back, this is at the front, then another 1.5 seconds. She's where she started. Does that make sense? Okay, so this actually takes 3 seconds, which is 2 periods, right? So you may want to say 0 to 1.5 seconds is back to front, and then 1.5 to 3 seconds is front to back. And that is kind of true for all of the pendulums. Any pendulum problem is like that. So you kind of got to be careful when you have a pendulum situation, how the question is worded. If the question is worded, how long does it take to get from one side to the other? That would be 1 period. Because on the other side, you end up at the same height. But if the question says, how long does it take to go like 1 full cycle back to where you started, that's actually 2 periods. Okay, there's nuance to these. Okay, how high did Morgan swing? How high did she swing? 2 meters, yeah, so that's the max value. Okay, and then finally, domain and range within the context of the question. So I spoke yesterday about the fact that, well, range, we can see what the range is because there's a min value and a max value. But I did speak yesterday about domain and how sometimes in contexts, domain is limited. Okay, so let's actually start with range here because that's maybe a little easier. We know a min height, we know a max height. Okay, that's our range from the min height to the max height. Okay, so instead of like y and x, maybe I'll use like h and t because we're using a context. So for my range, okay, min height is 0.8 meters. Max height is 2 meters. The variable that's in question is height. And my inequalities point that way. Yes?
When it comes to range, would the inequalities always go this way, or does it depend on the question?
The inequalities, when you have a double inequality, meaning that the variable is sandwiched between a min and a max, okay? The inequalities are always going to point towards the smaller value between the minimum value, okay? So if I had switched it around and put my 0.8 on the other side and the 2 on the left, yeah, then the inequalities would switch around, okay? For my domain, okay, well, what does domain, the horizontal variable, what does that represent in this context? Time. Okay, well, let's pay attention to this swing. At what time does this little swing ride last? What time does it start? 0. Okay. At what time does this little swing ride end? 6 seconds. So this swing ride only has a duration of 6 seconds. That's the domain. Okay? So domain and range. Domain is 0 is the minimum, 6 is the maximum. We're looking at time. There's my domain. Okay? All right, so that's one situation. The next situation is the wheel. The wheel. And you're looking at a specific height of a point on a wheel. And that also is cyclical, right? So the classic one is the Ferris wheel. How many of you guys have ridden on a Ferris wheel before? Many of you. Wow, you're brave. I had to once go on the one at Heritage Park. I got pressured into it by my children. I didn't really want to, though, because I get spooked by rides. But anyway, when you're on a Ferris wheel, you get on at the bottom, and you go round and round and round and round. And the height that you are at any given time is cyclical, right? You start at the bottom, you go up, you get to the top, then you go back down. And then you're bottom again. And then you go up, you get to the top, and then you go back down, and then you're at the bottom again. So anytime you're looking at the height of something on a wheel, that's going to be cyclical. And so it can be modeled using a sinusoidal function. Okay? Alexis owns a pickup truck. She puts a chalk mark on the outer edge of a tire so she could graph the height of the chalk mark over time as the tire rotates. The partial graph below shows the height of the tire as it rotates while driving at a slow, constant speed. Okay. So, A, based on the graph above, where did Alexis put the chalk mark on her tire? Where do you think she put it? Do you think she put it on the bottom, in the middle, at the top, somewhere in between? What do you think? The top? Yeah, it's at the top. How do you know? That's where it starts at. Yeah, when she starts driving, the chalk mark is at the top. Yes. So it's at the top. Okay? And that's because that's the initial height of the chalk mark. Okay? Determine the radius of her tire. Ooh. And what characteristic does this relate to? Okay, so let's think about this. The top of the tire is at 32. And the bottom of the tire, well, the tire's on the ground, so the bottom of the tire is at 0. Let's actually try and picture this. So here's the tire, and this is in inches. There's 32 inches. There's 0 inches. And here's the tire. Okay? It's supposed to be a circle. What's the radius of that? 16. Yes. Good. $16 inches. Okay. 16 inches. Now, what do you think that relates to? Yeah. Okay, so here's the thing with this scenario. 16 is both the amp and the midline. So let's imagine that, I'm trying to find something circular. Here's my water bottle, okay? So I'm gonna put it on this table. I don't know what, I can't measure it, but let's say this is about 3 inches across. You guys can see it over there. 3 inches across. Okay, so that would have a radius of what, 1.5 inches? Okay, so right now, the midline, it's on the table, is 1.5, right? Because the table has a height of 0, let's say. Okay, the radius is 1.5, correct? If I raise it off the ground, the midline's gonna change, right? Because it's getting raised. Do Does that make sense? So the middle is now like, I don't know, whatever this height is. What's the radius? Still 1.5. Okay, and the radius is from the middle to the top. What do you think that represents on the graph? The amplitude. Yes, the amplitude. And if you think about it, amplitude is defined as the distance from the middle to the top. That's the radius of a circle. Does that make sense? Yeah? Okay. So this is the amplitude of the graph. And anytime you have a wheel scenario, the radius is always the amplitude. Always. Because amplitude is distance from the middle to the top, or middle to the bottom. That's the radius of a circle. Okay, how long does it take for the tire to complete one full rotation? How long does that take? 1.6 seconds. Yeah, so top to top, right? That is 1.6 seconds. And that's the period. Okay. Domain and range. Okay, well, again, range, what's the lowest this wheel can be, or the chalk mark rather can be? 0. What's the highest? 32. So the range, 0, 32, height, right? And then the inequalities point that way. Okay, let's look at the range. I mean, not the range. We just did the range. The domain. Okay, so again, x here, or not x, but the horizontal variable, I'm going to call it t for time, represents time. What is the start of this little experiment? 0. Okay, what happens at the end here? Right here. What do you see? An arrow. So that she keeps doing this, right? Okay, this keeps going. It doesn't end. It goes on forever. It's still going on. So what that tells us in terms of our domain is that, not x, I said t is greater than 0. Greater than or equal to 0. Okay, there's no end. This is me making a mistake and not wanting to get an eraser out. Yeah. Okay, so what I'm going to give you guys now is I'm going to give you maybe 10 minutes to work on the next few questions on page 43 and 44. Okay, and those of you that are at home, I'm going to mute myself, and then we'll come back together. All right, so a couple of little points. You guys are doing really well with this. There's a few things that I just want to emphasize. Okay, amplitude, what does it mean in terms of context? Okay, so many of you guys got the median is 6 degrees. That's great, right? You take an average of the max temperature and the min temperature. Fantastic. Whoops. So this is 6 degrees. Okay, amplitude. The amplitude ended up being 18 degrees. Okay, what does that tell you about the climate in Edmonton? Well, if the average temperature is 6 degrees and you can go 18 degrees above or below, that's a pretty big variance, right? You can get 18 degrees hotter than 6 or 18 degrees cooler than 6, okay? That means in Edmonton, you're gonna like feel the seasons. And actually, I would even argue that maybe this is even greater than what this graph would suggest, because I think in Calgary and Edmonton are pretty similar. I think Calgary might be, or Edmonton might be a little cooler, but Calgary can get pretty cold and pretty hot in the summer. So there is a massive difference between the maximum temperature and the minimum temperature. And so we're going to have a very, very high amplitude in terms of our temperature throughout the year because there is a really, really big variance from the average. Okay, we're going to see very, very big differences from the average. Now, when you go closer to the equator, you kind of get the same weather all year round, right? You have the average, it's usually kind of warmer, but you don't go too much higher or lower from that. So you kind of have the same climate all year round, right? You don't have like snow in the winter and, well, you have kind of hot all year round, right? And when you go up to the North Pole, it's the same thing. You have the same thing all year round, except it's always winter. Does that make sense? Yeah? Okay. And then the other thing that I just wanted to address is on this question here, some of you guys didn't get to it, but it was the period, okay? This one has to do with, we're looking at height and time. Did I even give you a question here?
Yeah, it's on the last page.
Oh, it's on the last page. Okay, phew. The graph below is a tidal graph for Parksville, BC. Oh, Parksville, BC has really big tides. Okay, yeah, so we're looking at the height of the tide over time, okay? Now, the one thing that I wanted to talk about here is period. Can you guys see a full period in this graph? No. Okay, so how are we going to figure out period? Yeah. We could see half of it, exactly. So where would we, how could you determine half of it? Where would you look? Yeah. Min to max. This is half a period. And that's from 1 hour to 7 hours. 1 hour to 7 hours is a total of 6 hours. So if 6 hours is half a period, then a full period is going to be 12 hours. Sound good? Okay. Oh, I switched to purple. I like that. Okay. By the way, this homework down here, you guys should do that. Page 506. I think it's on the board over there that the people online can't see because it's on a whiteboard. But here it is. You guys can see it. Page 506. Do it. Okay. Here's what we're going to aim to get to today. I'm not sure if we'll get through all of it, but we're going to aim to do it. We're going to try and learn more about the equation of a sinusoidal function. Okay? We've looked at graphs. We've looked at how can we tell things like amplitude and median and period from the graph of an equation. Today, we're going to look at the equation of a sinusoidal function and see, okay, can we tell what those three things are from an equation? Could we match up an equation to a graph? That's kind of our goal. Okay? Now, I spoke about this briefly yesterday, but this is the form of a sinusoidal function. There are 4 parameters. Okay? A, B, C, and D. And basically, what these parameters are going to do is they're going to do things like move the graph up and down. They're going to maybe stretch it sideways or stretch it vertically, like, you know, stretch the accordion up or stretch it out or stretch it inwards, that sort of thing. And we're going to kind of figure out what each of these letters and the position of each letter in the function does in term to the graph of the function. Okay? Now, I said this earlier yesterday, but in this course, although we will touch on it briefly in terms of what does it actually do to the graph, you will not be responsible for knowing anything about it, which is this parameter C. Okay, not in 30-2. And what I can tell you right now is what that parameter actually does is it moves the graph horizontally from side to side. Okay? And actually what we've talked about in terms of midline, the middle of the graph, that moves the graph up and down. So yes, we do need to know that. Okay? Amplitude stretches it out vertically. We do need to know that. And then period stretches it out horizontally. because it makes the period longer or shorter if you stretch it horizontally. We do need to know that. The one that you don't need to know is moving it side to side. If you have a situation where the graph is moved side to side, that piece will always be given to you. Okay, so what we're going to do is we're actually going to play around with these three parameters, A, B, and D, one at a time. So we're going to look at them, at changing them one at a time, but not changing anything else. Okay, so please take out your graphing calculators, and the first one that we're going to look at is the parameter A, the number that's in front of sine. And we're going to look at these three functions, y equals sine x, y equals 3 sine x, and y equals a half sine x. Okay, and actually, we've already graphed y equals sine x. Okay, so that shouldn't be surprising, and I'll just kind of remind you, I'm going to flip back a little bit. We did that yesterday, all the way back here, over here. This is what it looks like. Okay, so it has a period of 2 pi, starts at 0, and it goes to 2 pi. And that's because, remember, when you start at 0 and you go all the way around a circle, that circumference is 2 pi. So there's like 2 pi radian is equal to 360 degrees. And then the amplitude is 1. So it goes up to +1 and down to -1. Okay? So actually what we'll do is we'll put that one in right away. And of course, we'll look at this on a graphing calculator as well. But the first one is y equals sine x. So that has period of 1. No, not a period of 1, an amplitude of 1. So I'll put in 1 and -1, and here's 2 pi. Okay, and here is, just divide this into 4 so that I can kind of guide my graph. And it starts like this, and it goes like that. Okay, so there's the first one. But let's actually graph all three of them on a graphing calculator. So we'll take them out, and we're going to go to y equals, and we're going to have sine x 3 sine x and a half sine x. Okay, and what I'm going to do, just because I have that drawing on my, in my notes already, I'm going to make my window settings similar to what I had there. Okay, so what I had there was 0 to 2 pi along the x-axis. So my x-min was 0, and my x-max was 2 pi. And maybe I'll keep the y-min at -4 and the y-max at 4. Okay, so I'll just give you guys a second to sort of catch up with that. Okay, so x-min 0, x-max 2 pi, y-min -4, y-max 4. And I'm going to hit graph. So there's the first one, there's the second one, and here's the third one. Okay? Now, let's talk about a couple of things that stay the same. So the three sort of characteristics of the graph that we talked about yesterday were midline, amplitude, and period. Midline, amplitude, and period. Midline was the middle of the graph. Amplitude was the distance from the middle to the top or to the bottom. And the period is how long does it take to complete one cycle. Do any of those three stay the same for all three of these? Are any of these the same? Are any of those three? Either the midline, the amplitude, or the period? Are any of them the same? Yes. The period's the same, yeah. They all do one cycle in 2 pi. Okay, so period doesn't change. Okay, is anything else the same? Yeah. The midline's the same, yeah. The middle of the graph is always the x-axis. All right, so what changes here? The amplitude, yeah. Okay, so the first graph was sine x, and that was the blue one, and that has an amplitude of 1. You can see the scale right here, which is at 1 on the graphing calculator. Okay, so the max point is at 1. Okay, the red graph was y equals 3 sine x. What is the max value up here? What was that? 3, yeah. And the black one was a half sine x. What's that value? Half. Yes. Good. Okay, so let's record that. Okay, so we had 1, 2, 3. So we had y equals, this is y equals sine x. And in fact, I'm going to be even more specific than that. I'm going to add something in there that I don't have to put in. I'm going to put y equals 1 sine x. Okay? I'm going to put in y equals 3 sine x. Oh, I better put in down here. -2, -3. Y equals 3 sine x. Okay? And then y equals a half sine x. That's this guy. Okay. And again, I'm going to cross this out because I want to be very, very explicit here. Y equals sine x is the same as y equals 1 sine x. What is the a value here? Almost like a coefficient of sine x. It's a. Or sorry, thank you. It's 1, yeah. So here, a equals 1. What's the amplitude of y equals 1 sine x? What was the amplitude of this guy? 1. That's right. What's the period? How long does it take to do one cycle? Not 2, but 2 pi, yeah. Okay. Y equals 3 sine x. What's the amplitude of that? Three, yeah. Right? Because this here, distance from the midline to the amplitude, to the max is 3. Right? Okay, and the period? 2 pi. And then finally, y equals a half sine x. What's the amplitude? Half, yeah. 0.5 or a half. And the period is still 2 pi. Okay, so what does the parameter a do? Changes the amplitude, yeah. The parameter a is the amplitude of the function. Okay, great, we found out one of them. Let's move on to another one. Okay. We're going to do these ones one at a time. Okay? Well, we've already actually done y equals sine x. So let's just redo that one. Y equals sine x, we know 1, negative 1. Oh, that's a little bit low, but whatever. And the period is 2 pi. Okay? Ugh, maybe I'll erase that in a sec. Okay, there we go. Oh, sweet. I like purple. I'm going to stick with purple. Why not? You can teach an old dog new tricks. Okay, so that's y equals sine x. Okay, nothing new. We just did that one. Amplitude, we already wrote that down. That's 1. Period is 2 pi. Okay, now let's take a look at this next one. Y equals 3 sine x and y equals a half sine x. And actually, before we do that, I should mention what we're doing now here is which of these letters are we playing around with? We just played around with A. Which one are we playing around with now? B, that's right. Yeah, so we're going to try and figure out what B does. Okay? All right, so let's take a look at y equals 3 sine x. Okay, so I'm going to go y equals clear, clear, and clear. Whoops. And y equals, or no, not 3 sine x, sine 3x. Big difference. Sine 3x. And I am going to graph this. Okay. Now, just looking at this graph, okay, what is the amplitude? Right, midline's still the x-axis, we can see that. What's the amplitude? It's still 1, okay, so amplitude isn't changing. Okay, is the period 2 pi? No, okay, in fact, normally the period is 2 pi. We can fit 1 period in 2 pi. How many periods are happening within 2 pi here? Let's count them. We've got, tell me when I get to the end of the period, okay? Tell me when to stop. Oh, come on. Really? All right, everyone look up. Okay, here's my starting point. Tell me when to stop when I get to the end of the period, okay? Okay, that's 1. Okay, do it again. 2 and 3. I have 3 periods within 2 pi. All right, interesting. Let's write that down. So here, amplitude is still 1 and negative 1. Here's 2 pi. And what we saw here, I'm going to divide this into thirds. And I got to tell you guys, when you're drawing these, you kind of have to, almost like the faster you do it, the better it comes out. Okay, so 3 periods happened within 2 pi. So let me just, okay, so we're going to go 1, 2, 3. This one should be a little lower. There. Okay, so what we have here is 3 periods in 2 pi. This is 1 period in 2 pi. Okay, well, if we have 3 periods in 2 pi, if we wanted to figure out what one of them is, we could just go to our graphing calculator and figure that out, right? The end of the period actually happens at this first 0. So we could certainly figure it out that way. So I'm going to just find number 2. I'll find the first 0. over here. So that's the left. There's the right. And it's at 2.09. So this happens right here. That's 2.09, okay? This is 1. Okay, I want you guys to put into your calculator, we took 2 pi, and how many chunks did we divide it into? 3. Put into your calculator 2 pi divided by 3. Tell me what you got. Yep. 2.09. Yeah. So this is actually 2 pi divided by 3. What was our b value in this function? 3. Okay. What was our b value in y equals sine x? Y equals sine how many x? What's the coefficient of x here? 1x. 2 pi, we had 1 period in 2 pi. This is 2 pi divided into 1 chunk. Okay, let's look at another one. Let's look at y equals a half x. Clear? No, not y equals a half x. Y equals sine a half x. A half x. All right, there we go. And I'm going to graph this one. Okay, so here's what we see for this one. Firstly, okay, let's do this amplitude thing again. What is the amplitude of this graph? Here's the middle. The x-axis again. What's the amplitude? Still 1, yeah. Okay. So this is what happens. Here's 0. Here's -1. Here's 1. Here's 2 pi. We actually only see how much of a period do we see in 2 pi? Not 1, because it'd have to go all the way to the bottom as well. Half a period. We only see half of it. Yes. Half a period in 2 pi. Well, if half a period is 2 pi, what's the full period? 4 pi. Yeah. Okay, put into your calculator 4 pi divided by, now in brackets, you got to go 1 divided by 2. No, not 4 pi. Sorry, silly me. 2 pi divided by 1/2. Tell me what you got. 12.56? Okay, you got 12.56?
There's also another number between not 6, so it's
12.57? Okay, put into your calculator 4 pi. Tell me what you got. 12.57, right. So these are the same thing. Oh, yeah, and the amplitude's 1. Okay. All right, now, is the b value, I'm going to get to your question in a second, is the b value the period? The b value was 1/2. Was the period 1/2? No. It was 12.57, or 4 pi. In the previous one, the b value was 3. Was the period 3? No. The period was 2.09. In the first one, the b value was 1. Was the period 1? No. The period is 2 pi. Okay. Is b the period? No. Does b affect the period? Yes. Good. Okay, so b is not the period, but b affects the period. Okay? And in fact, what we saw here was that the period was always 2 pi divided by the b value. That worked out every single time, right? Here the b value was 1. The period was 2 pi divided by 1. In the second example, the b value was 3. The period was 2 pi divided by 3. And then third example, the b value was 1/2. The period was 2 pi divided by 1/2. Okay, so the b value is not the same as the period, but it is related to the period. And it's related to the period this way. Period equals 2 pi divided by b. Okay, this is on your formula sheet. Now, every time, I promise you I'm going to ask you a question on this, and well, maybe this year will be different, but usually 1/3 of the people say that the b value is the period. So try not to make that mistake. Let's change the stats, just like we're trying to do with COVID. Okay, one more. Let's see if we can get to it. I think we can. Last parameter. What do you think this parameter is going to change? What haven't we changed yet? The midline. Yeah, let's see if it does. Okay, and that's d, right? Now we're changing the d value. So we got 3 functions. We got y equals sine x. We got y equals, I can't remember, sine x plus 2. And we got y equals sine x. Sine x minus 1. Okay? And I'm going to graph these again. And surprise, surprise, that's exactly what happens. The graph moves up or down. Okay? So for the blue graph, this is the one that we've kind of been using as our control, right? In science class, you keep something as the control all the time when you're doing experiments. That's what we're doing here. That's our sine graph. The midline is at 0 because that's the x-axis. For the red one, where's the midline for the red one? It goes up to 3 and down to 1. Where's the middle of it? 2, yeah. It's at 2. And then for the black one, where's the middle of the black one? -1, yeah, because it goes up to 0 and down to -2. So the middle of those two is at -1. Exactly. Okay, so we'll just quickly jot that down. I'm trying to rush a little bit because we're about to run out of time. So I appreciate your... Okay, so here's sine x. There's 2 pi. 1 to -1, and then we had y equals sine x plus 2. So that went up from, here's 2. So it's going to go basically from 1 to 3, because the middle, and you can actually do this if you want, draw yourself like a dotted line to kind of get the midline so it can help guide you a little bit. And then for -1, here's the midline as well, right? And then it's going to go down to -2. Exactly. Okay? So does the amplitude change in any of these, by the way? The distance from the midline to the top. No, that's always 1. Yeah. So the amplitude for all of these is 1. Okay. Did the period change? No. Period is 2 pi. That makes sense because the b value is the same. The b value is always 1. Midline changes though, right? So for y equals sine x, the midline's at 0. And for y equals sine x plus 2, the midline is at 2. And for y equals sine x minus 1, the midline's at -1. Okay, so what effect does the parameter D have on the graph? Well, D is the midline. Okay, here's an example. We're going to do this one and then we'll end it for today. Okay, and this is where your quiz is going to cover up to, by the way, on Thursday. Basically up to, can you come up with an equation? Okay, up to this lesson. Okay, determine the amplitude period equation of the midline, domain and range of the graph of the function y equals 1/3 sine 2x. Okay, so what you may want to sort of keep in mind here is that generally these functions look like this. And remember, you're not really responsible for C, so just leave that out, because there's no C value given to you. Okay, what does A tell us? Amplitude. What does D tell us? Midline. What does B tell us? Not exactly the period, but it affects the, information about the period, right? So the period is 2 pi over B. Okay, so we can say what the amplitude is. It's 1/3, because that's the A value. What's the midline here, by the way? What's the D value? It's 0, yeah, we're not adding anything on the end. So the midline is 0, which means the equation of the midline, horizontal line at 0 is y equals 0. Period, what's the period? The B value's 2. Don't graph it. 2 pi over B, yeah. 2 pi over 2. And these cancel, which is pi, yeah. Okay. You could write it as pi or 3.14, I don't really care. Okay, yeah, pi is more of an exact value, okay? Now, domain and range, listen, you could graph it if you want, but think about this. The midline is at 0. Here's pi. The amplitude is at 1/3. So from the midline, we're going up 1/3 and down 1/3. Okay? If you can picture that, hold on. You'll be able to determine the domain and range. Okay, before you go, I want you to do these practice questions on page 48 for homework. Page 48, got it?